up part 1. We're going to finish chapter 3. And then we're going to start right here on part 2 on correlation, causation, and confounders. So we're a little bit behind, but we'll try to catch up this week. Now, one thing you might notice is that the Wednesday homework 1 due date has been extended until Friday. So you'll be able to do it by the end of this class. It was just because we got a little bit behind schedule, so I extended our due date. Any questions on this? All right, so let's just go turn to your books on page 9 where we left off. And let's go to the document camera here and remember what we were doing. Okay, so let's just look at this problem again. This is the last one we did. And we saw that we were given in this problem that the null hypothesis is that the number of study hours that students typically spend, the average study hours in this professor's class was 6 hours. We were given that with a standard deviation of 4. That's what we're given, 6 and 4. And you think that that's not true. You think it's much greater than that, more like 8 hours. So you just want to see that what would happen if you sampled, if the true value really was what you believe it to be, 8 hours, and the average in the class of 2000 really was 8 hours, and you want to prove that to your professor and say he's wrong. So your alternative hypothesis is here. That's a 2-hour difference, quite a lot more time that you guys are spending. Now, the professor said the standard deviation was 4. So we did this sampling distribution here, and we decided to set the conventional type 1 error, the probability right here, this type 1 error, we decided to set that at 5%, which translated then into a middle area of 90%, because it's 5% on each tail, and a z-score, we looked up a middle area of 90, and we got that z-score of 1.65. Now, that's the z-score, and we translated that into, that's in pure unit, that's unit free, but we want to change it to hours. That's not 1.65 hours, that's 1.65 standard errors above the average, above our expected value under the null. Our expected value under the null is 6, and so it's 1.65 at 6, starting there, plus 1.65 times the standard error. Now, how did we get that standard error? We got that standard error for the average. Each time we take a sample of 16, we're going to get a somewhat different average of those 16. Sure, and how much is that going to bounce around by? That's our sampling error, our standard error for the average, and we know that's depends on the SD, the variation inside the box, and our sample size. The bigger our sample size, the more precision we have, the less sampling error. Okay, so that's what we've got. That we got 4 divided by 16. That's where we got this 1. That's not one. That's 1 standard error. Okay, so we translate it to 7.65. Then under the null is what you claim right here. You claim, excuse me, under the alternative, when the alternative hypothesis is true. This is when the null is true, but you think the real truth is this, that there's another null box, right? And the real truth is you're really sampling from an average that has 8 hours, but you're keeping the standard deviation as 4. So you're really drawing 16 out of this box. It's the same as that one. It just looks like this. And of course, since our sample size is 16, we still have the standard deviation is the same. We still have the same standard error. So it looks like this, right? So now you say, okay, now you want to specify another type of error. That's the type 2 error. When this is the truth, excuse me, my mic fell off here. Okay, so when this is the truth, when you're in this situation, which you believe to be in, then of Of course, you're going to be over the cutoff, but what's the chance that when you're in this situation, you're going to make the type 2 error, and your sample is, even though you're sampling from this box, your sample is going to fail to detect that big a difference just by the luck of the draw. And we said we wanted to figure that out. So that's what we're trying to figure out here. And what we did was we said, okay, we knew everything, so we said, okay, we translated this Z, our observed value of 7.65, this difference right there, what is that in terms of a Z-score? This is probably confusing to you because look at that error. That should be negative 0.35 there. So we saw that that was 7.65, that difference, 7.65 minus 8 divided by our standard error. We saw that that Z-score right there is negative 0.35. Then we looked at the back of the book, saw that corresponding to a middle area of 27. That's how we got that right there, our type 2 error of 36.5, which means a power of 63.5. Okay? Any questions on that? You did homework on that? Is that, remember, did people do okay on the homework? Raise your hand if it was difficult for it. If it was okay, if you understood it, raise your hand. Good. Okay, so I just went over that problem again. But now, so we did this, and with a sample size of 16, and we saw we had quite a big type 2 error and quite small power. What if we wanted to increase that power and reduce this type 2 error? So that brings us to our next question, chapter 3, and that is, so in the previous example, you were given the sample size, n equals 16, and asked to calculate the type 2 error. Now, usually you have to go in the opposite direction. Usually, you have to calculate n. You have to figure out how big a sample you need to achieve set levels of the type 1 and type 2 errors. Okay, and this is why, because, well, the most common reason is because granting agencies request that you plan your studies with alpha, the type 1 error less than or equal to 5%, and the type 2 error less than or equal to 20%. So which means they want you to have a power greater than or equal to 80%. And you would want this even so, I mean, you don't want to go through the trouble of doing an experiment and having a big risk of failing to detect an effect that's really there. So even if it wasn't, if this wasn't, these conventional limits weren't set, you yourself would want to, when you're planning any kind of an experiment, you want a big enough sample size to detect the difference that you care about. In this case, the difference was that 2-hour difference. It's really 8 hours. If it was 6, you might not care about a difference that was like just a half hour or 15 minutes. Would you go, if you were in that situation and the professor estimates 6 hours of homework a week and you think, oh, it's really 6 hours and 15 minutes or 6.5 hours, you probably wouldn't care about that. But when it's as much as 8 hours, 2-hour difference, then you care about it. So the hypothesized difference is something, it's a difference you care about detecting. Okay. So now we're going to go, so now we're trying to find n given a particular power. Before we were trying to find the power given n. Okay. So let's see, okay. So in other words, you need to find the smallest sample size that will detect an effect as large as the one you specify, given the type 1 and type 2 error limits that are set. So, and then I said, how should you choose your alternative? And as I just said, that depends on what difference you care about. What's the minimum difference that's important to you? I mean, if it was, let's go back to our example. If you realize everybody's spending 20 hours a week, well then you probably don't need to do it significance test, and you don't need a very big sample size. If it's an overwhelming difference, you just sort of, it's obvious to our intuition. So what's the smallest difference that you would care about? And maybe that would be like a 2-hour difference. That's what I was hypothesizing. It just depends on the situation. All right. So now let's just do the same example again. And how many people would you have to sample to get a power equal to 80? Okay, 80%. Sticking with the same alternative. So we have everything the same. So it's still 6 and 4 here, right? So we still have this situation where in standard units, in z-scores, this is unit free, and here we have it as our value in hours, those are our actual units, it's 6. That's our null, and this is what the normal distribution looks like in standard units. And now, what we're doing is we're setting alpha again equal to 5%, so that's 5% in this tail, and we look again, we know now that we just went through this, that means our z, our critical value at alpha equals 5% is 1.65. So this right here is 5%. All right, so we've got that. And now to get our hours here, this right here, this value is going to be what? That value will be equal to, well, 6 plus 1.65, 1.65 what? Not hours, but 1.65 standard errors. In each standard error, so let's just write standard error. Now we can't put, we don't know what to put in here, right? I mean, what is our standard error? This is equal to 6 plus 1.65 times SD over the square root of n. So that's what we have there. We can simplify further. Do you want to simplify further? We could, and this would be equal to what? 6 plus 1.65 times 4 divided by the square root of n, which is equal to 6 plus 1.65 times 4. Sorry, that looks very difficult to read. 1.65 times 4. So that's equal to plus 6.6 over the square root of n. So that's what we have there. I can just write here 6 plus 6.6 divided by the square root of n. All right. We don't know what n is. But now, under the alternative, what do we have? Well, now, under the alternative here, 0. And this is 8, right? And now we're going to set beta. So let's look. So now, draw the normal curve and find z for power equal to 80%, because we have to set we have to find what the z-score is for power equal to 80%. So for 80%, power means, this is your type 2 error of 20%. That means we want, here we specified 5%, now we're specifying 20%. Okay, you understand? So if we specify 20% in this tail, use this, we have to find the z-score corresponding 20% in this tail, we mean 20% in that tail, right? Which means it has to add up to 100, so we have 60% in the middle. So what we want to figure out is what the z-score is corresponding to a type 2 error of 20%. Yep.
We can move over a little bit.
Oh, yeah, thank you. Thank you. So what we want to do is we want to find out the z-score corresponding to a type 2 error of 20%. All right, so where are we going to set this one? This is -1, -2, -3, 1, 2, 3. So we just want to know where that is. So we look up, go back to the book here, we look up a middle area of 60%, and that is, we're just going to round a middle area of 60%, and so it's about 0.85. Okay, so that's between 0.85 and -0.85. Okay, so clearly we're on this side, So it's about right here. Space, okay, we'll shift it over, it looks like that. So now we have Z beta is equal to negative 0.85. Between that and 0.85, 0.85 is the 60%. And this is our type 2 error that's specified. All right, so now we have, okay, so now we know our two Z-scores, right? And but we can only, so what's this value right here? What's this value? I'll just write it here. This is going to be 8. This is our value right here. This value, I'll just do it quickly, is going to be 8, what? Minus 0.85 times SD over root n, over our standard error. And we know that the SD is 4, so we're going to plug a 4 in for there, 4 hours. So we have 8 hours. This is as a value, 8 hours minus 0.85 times 4 over the square root of n. So that works out to be 8 minus 3.4 over the square root of n. So we have these two values. Whoa, yeah, sorry. Sorry about that. Okay, does everybody understand? Questions so far? Okay, so now, what do we want to do? Well, this is, we want to figure out what n, we'll set these two equal to each other and solve for n. So we get 8 minus 3, so this is what we're doing right now. Okay. So we have 8 minus 3.4 over the square root of 9 is equal to 6 plus 6 over the square root of n, excuse me. Over the square root of n. Okay, does that make sense to everybody? So what do we get when we do that? When we do that, we'll get what? 8 minus 6 is equal to 6.6 plus 3.4, which is 10 over the square root of n, right? Isn't that right? So what's the square root of n? The square root of n then is equal to 10 over 2. So n is equal to 25. Any questions on that? All right, so now, I think that was for this specific problem, but let's just sort of think about, I think it's easier to think about what we're doing here. And with what we're doing, if we turn the page, I added this page because I thought it might help. This is the first time I'm doing this with, but I think this will be helpful to people maybe, so they don't have to understand it. So basically, if we draw the two graphs together, you can think of it this way. In general, you can think of it this way. This is your null hypothesis, right? This is your null, and your null hypothesis has, so here's 0 on your null hypothesis, and here's 0 as a z-score on your alternative hypothesis. Okay, so that's what it looks like. And now, then what do we have here? We also have, so this is as a z-score, right? And then we're going to do it as actual hours here. So this, in this case, our hypothesized null was 6. And what was our alternative? Do you remember? This was in terms of our actual values here.
8.
Unit. Do you remember? What was it? 8. All right, so look what we're doing here. Watch this. What is this distance here between this? This is a distance. This distance is 2, right? This distance right here is 2 as a, that's our hypothesized difference. We hypothesize a difference of 2. But what is it in terms of z-scores? Can you see what it is in terms of z-scores? Well, this z-score from here to here, from here to here is 1.65, correct? That was 1.65. Isn't that distance 1.65? That far? Is it z-score? Is it?
Yeah.
Yeah. What is, and then, let's think what this distance is. Do you remember what would this distance be? If we set, this is when we're setting alpha is equal to 20%, and we're saying beta, is equal to 5%, and beta is equal to 20%. So this was 1.65, that was Z alpha, and Z beta that corresponds to that is what? We said it was negative 0.85. So what do you think this is, just as a distance? This was what? The same cutoff here was Z alpha equal to 1.65, but it was what? Z beta equal to negative 0.85, correct? Isn't it the same cutoff? We want this right here to be 20% and this to be 5%. That's 20%. This is our 5%, okay? So that's what we've specified. So this distance right here, isn't that 0.85%? Boy, is that easy to see? From here to here is 1.65, and from there to there is 0.85. Right? It's a distance, isn't it? What would you think the distance is as a z-score? From here to here is 1.65. From here, going from here, maybe I should do another axis. Going from here to there, that's negative 0.85, but just as a distance. How far are these apart in z-scores? That's what I'm trying to get you to see. You look blank. You gotta look at what it looks like. Does it look that bad that it's hard to see? I'm going to get up there and so I'm going to show you up here. I don't know if it helps. Okay, guys. This is not hard. This is super easy. Please don't let me overcomplicate it for you, because this is really obvious. 2. A distance is 2, right? 8 minus 6 is 2. Now we're just trying to do that same distance, not as hours, but as z-scores. This, from here to here, 1.65, correct? Now, from here to here, to make this 20%, we had to set that. We found out that that's negative point, that distance, just as a distance, is 0.85, is it not? You can't have a negative distance. I'm just talking about how far apart they are in terms of z-scores. You got it? Yeah. So now we have 1.65 plus 0.85. That's our distance, 2.5. Yeah?
If the standard error is 1, shouldn't the distance between the z-scores also be the same distance from...
We don't know this. If the standard error is 1, that would be true. But that standard error being 1 depends on a sample size of 16. Remember? Now our whole point, excellent question. Our whole point is, okay, we hypothesize, we know this distance. That's the distance we care about, 2. All right, let me go back and write it. There's a number. So we know that's 2. This is the whole deal. So we know our difference that we care about. The alternative, that difference, that's our difference in values, that's 2. And we're saying we also know it as a z-score, z alpha plus z beta. It's, this is our difference in standard units, or in z-scores. Okay, I'll say in standard units. Unit-free in standard units, z-scores. That's our difference. Well, so let's think what this is. This is 8 hours minus 6 hours. And this is a z-score of the distance from here to here. To make our type that error at 5% is 1.65. And then we want this, just because we want our both errors to be small, right? If we say that's 20%, then we have to move this one even another 0.85 beyond that, right? If we wanted to make them both 5%, we'd have to go 1.65 and push this one all the way over to 1.65, so they both were 5%. And then the distance would be twice 1.65 or 3.3. Okay, so this is in z-scores. Okay, so we have 2 hours here. And now we don't have hours here. We add those together, we get 2.5. It's unit free, it's just, what do you call them? Standard units, whatever you call them. This is an hour. Well, so basically, how do we convert from these standard units to actual units? Well, that's what the standard error does. It tells you how many, this is like a conversion factor. This tells us how many, this is in hours. This tells us how many hours is in each standard unit. So this is like how many, in this case, how many hours per standard unit, right, per z-score. And this is a standard unit, or how many hours per z-score, this is a standard unit. That's all it is. These are unit free. We have hours, and we know these two, and basically this is our error. This is our sampling error. Sampling error. This right here is our sampling error, and it's for the average, and so it's standard deviation divided by square root of n. So we have to know, we want to know, why don't we solve for that? So we say we know now that our standard error has to be equal to what? 2, this is hours per standard units over 2 hours. See, the units match up for 2.5. 2 hours per 2.5 standard units. Just, and we know this is hours per standard unit, that's what it is. How many hours is in one z-score? Okay, so I just want to show you these units. So now you have this, so what is this? You have to have a standard error of 0.8. Not 1 anymore. What it's saying is, remember, I'm really glad you brought that up, with a sample size of 16, we had too much type 2 error, right? Our standard error was 1. Now we're saying, okay, if we want to reduce our type 2 error from previously it was 36.5 down to, what is it now, 20%? Well, then we have to reduce our sampling error from that 1 to 0.8. We know what our sampling error is. So now we just have to say, okay, how big an n will give us that sampling error? We'll make it that small. Does that make sense? It's really not, what you're given is 2 things. One is this. To make them equal to each other, you have to use this conversion factor. Okay? So this is basically the idea. You know the distance in values, you know the distance in standard errors, and you have to convert them. So this right here, you know the distance in value, you know this distance in z-scores, and all you want to do is figure out how to make your standard error, what your standard error has to be. Okay? So this is your conversion factor. You can't say, otherwise it's like 2 hours equals 2.5. You have to multiply by your standard error. Okay? From standard units to hours. Okay, so we want a standard error of 0.8, right? So that's what we want. So what do? We say SD over the square root of n has to be equal to 0.8. And we know that the SD is 4. So we say 4 over the square root of n has to be equal to 0.8. That's 4/5. 4/5 is 0.8, so the square root of n has to be 5. So n is equal to Basically, why I'm doing this is what? If it does, I want to see if it helps you. The idea is this. If you wanted, let's just draw another picture and see if this helps you at all. Like if you wanted to reduce, like, you have two curves. One is, and you specify this, let's just keep this at 5%, so that's 1.65. Let's say we wanted the other, let's say this is, here we have 5% and 20%. Whoa, sorry guys. Okay. So here we have 5% and 20%. That was given to you. You tell me what you want. Do you want to make this smaller? Tell me what you want to reduce it to. Let's say you don't want 20%. You want something littler. You want 5% on both? So what would that mean? Okay, here's my null. Okay, I want 5% on each. That means I'm going to have to draw this other curve. So it looks just like, so that's 5%, and it looks just like the same curve like this. Okay, and that would also be 5%. So, and here's 8 and 0. Okay, so now from here to here is 1.65, and then this would be negative 1.65, wouldn't it? If I wanted this to also be 5%. Maybe this is easier to see. So from here to here you have 1.65, then you have another 1.65. So now what do we know? This is because you're given this. You're given, and this is how it usually is, your alpha, your beta, 5%, 5%, your difference, that's you're given, or you set that. And one other thing, your SD. Okay? And all you're trying to figure out is your sample size. Okay? So, you have this as your difference. Your difference is equal to 8 minus 6. Right? That difference too. Now, in terms of z-scores, what is it? That's what this does for you. In terms of z-scores, it's what? Difference in z-scores. Oh, now you're getting it. Difference in z-scores is equal to 1.65 plus another 1.65. Now do people see it? 1.65 plus 1.65, which would be what? Isn't that 3.3? Okay. Now you have these two things. How do you connect them? One is in like a standard yardstick that applies to anything. It's unit-free, height, weight, anything. This has no units. This has units. This is out. This is your particular problem. You want to match the two up, okay? So, what you say is this difference, your hypothesized difference that you call that, is equal to your z-score difference, and you call that z alpha plus z beta. Why not minus? Why not minus? Well, really, it's just because it really is the alpha minus a negative beta. But it's much easier, it's just this distance and that distance, which are both positive. Does that make sense? Okay, so you have these two things. And then this is your conversion factor, your standard error. This is in hours per standard unit. This is always in standard units. And this is always like in hours or values. So you see how those cancel out? This changes it from standard units into hours. This is what you use. Does this make sense now? This is all you're doing. And the reason why I'm showing it this way, because this standard error is going to change. It changes, it's ST over square root of n, right? For one sample, only one sample here, for the standard error for the average, we have SD over the square root. I don't know, I gotta get a new pen. Okay, so that's SD over the square root of n. But what we're going to see in our next problem, for a 2 sample, it's going to be different. And for a percent, it's SD over the square root of n times for standard error for percent, we have SD over the square root of n times 100 for, you know, a two sample difference in averages. See next page. We're going to do that. It's going to be the standard, I'll give it to you right now, but it's going to be different for different things. And it would be the square root of your SD squared over the square root of n squared plus SD over. We'll do this on the next page. You know, depending, okay? So it's different for everything, but this is the basic idea. All right? And then what do? From this, it's really different. So then the next step would be, okay, so you just solve for your standard error, and this you can get a number for. This is just going to be what? Your difference divided by your Z alpha plus Z beta. Right? So now you know this, and boy, this, I just bought this pen. This pisses me off. You know, I just bought it, especially for this class, and now it's no good. Try a different one. All right, so this, what, I wanted to put a box around this. And basically, you have, when you're given all this, when you're given all this stuff, like you usually are, what that tells you is what the size of your sampling error has to be. And then your sampling error depends, then you know that, and the smaller this is, the bigger your n has to be. The bigger, and that's all you're doing for all these power calculations. So let's go through it again, because I know you want to see it exactly how it relates to the formula you used on your homework. So let's go through and we'll get that. So let's see, this is what we're doing, da, 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 da. Okay, so now we're on, I just want to have you find the general formula that might be easier for you in terms of n. So now just to show you how it's really the same thing. So let's go through it again, and now I think you're going to understand it. So we had a 6 for our null. Okay? And then we had an 8 for our alternative, same standard deviations. And okay, so this is 0, and that's 6. This is 0, and that's 8. And we said Z alpha is equal to 1.65. And we're not going to do 1.65 again. We're going to do the standard 20% thing, which was Z beta equal to negative 0.85. Okay? Got that? All right. So, now, I'll show you how it works out to be the same thing, what we did before. So now we said this. We said this right here is 6 plus 1.65 times our standard error. And we said this one right here is 8 minus, because we're going in that direction, 0.85 times our standard error. And so the way that we can get the same general formula that I showed you intuitively by doing this is we can say, okay, what is our general formula? We're just going to set those two equal. So we have 8 minus 0.85 standard errors. That's equal to 6 plus 1.65 standard errors. Correct? All right, now look what happens. When we just solve for the standard, we're going to get the same thing. Here we say 8 minus 6. We'll bring this over to that side. And that's equal to 1.65 plus 0.85. That whole thing times your standard error. Right, and that's what we have. Here is D. This is your hypothesized difference. Right? This right here is D, we'll call it, which is really just our alternative minus, C, minus our null We call it, think of it as our hypothesized difference, our effect size. This is the effect size, 2 hours. And here, you can see, this is just Z alpha plus Z beta. So that's our difference in z-scores. That's our distance in z-scores, okay? Hypothesized difference, and that's our difference in z-scores. I mean, it really is, it's because that's negative, so it's minus a negative. So this is our difference in z-scores, I hypothesize it. This is our difference in z-scores. And there's our standard error. That's our conversion factor, the standard error. Okay, does that make sense? Does that help? You know, so then we can say the standard error is just our difference, D over Z alpha plus Z beta. And then we can say, if, like in this case, if the standard error is equal to SD over root N, well then what do we have? Then we have, what? SD over the square root of N is equal to D over Z alpha plus Z beta. And then you can solve for N. So if we solve for N, what would we get? You cross multiply, you solve for N, then you square everything. So you would get N would be equal to, D would be in the denominator, right? And everything has to be squared. And then we'd have Z alpha plus C beta squared. This is just algebra times SD squared. And that's the formula. That's the formula you could use for that particular case. Okay? All right. Now, any questions on this? Okay. So now what if usually usually the programs for some reason just do by default these two-tailed alternatives. So instead of saying having an alternative that's directional, like it's greater than, it's usually that it's just not equal. Like, let's say if we didn't know whether it was greater, or if we didn't know whether it was positive or negative. Basically it's this, okay? So we've been doing, if you have, instead of saying, okay, I know which direction, and we're doing a one-tail, now we're going to be doing a two-tail. A two-tail at 5% means 2.5% in each tail instead of 5% in one. It means you don't know which way it's going to go, whether it's going to go this way or it's going to go this way. You just think that it's not going to be the same, so it's just as the null. So the alternative could be either this far away, this high or low. And so then you look for 95% in the middle. So you look up, so your critical value would be, instead of 1.65, you'd have to have 95% in the middle. So it's between 1.95 and 2. Sometimes we just round to 2, a lot of people do, but usually people use 1.96. So we'd say, okay, well then it's between 1.96 and 1.96. Okay? So instead of getting a critical value of 1.65, we'd have 1.96. You'll see that a lot for your critical value. That's if you were doing a two-sided alternative. All right, so let us now, on the next, now we're going to go to a two-sample. Look at the standard error for a two-sample problem. And so often you have, you're comparing two samples, and so how would our formula change? We often want to know if two groups differ. Right now, what am I asking? I'm asking whether this one sample, just differs from some claim that the professor made, that he said was going to be, our null was that the population average of the whole class was 6 hours of studying time, and we thought our null was that, no, it's 8. So we were to have one sample. We took one sample and compared it to the claim that the professor made. But often what we want to see is not that. We want to see if there's a difference between two samples. Like, let's say you have two classes. This comes up all the time. Where are two versions of an exam. And the professor claims it's equivalent. And of course, the averages between the two groups of students who take it aren't going to be exactly the same. But the idea is that within random variation, it's the same, right? Within sampling error. So basically, that you would test the null would be that there's no difference between the two versions of the exam. And the alternative would be, yes, there is a difference. So we'd have two samples. You compare two groups for treatment and control. Does that make sense? You got it? So how does the sampling variation, how does the standard error change? Well, in Stat 100, of course, we have a different formula because we have two sources of error. We're sampling from one population. We're taking a sample from one population and a sample from another population. So we have two standard errors. And so what are we doing here? So if we assume that we have equal standard deviations and equal sample sizes, let's make it super simple, okay, then what would be our formula for the standard error for the difference? Well, it would be, what? The standard error for the difference is going to be the square root of SD, let's say their averages over the square root of n squared, that one, plus S for one sample. And they're going to be the same standard deviations, the same n. See, I'm just going to make ST1 equal to ST2 and N1 equal to N2. Okay, and that is just what? Well, squared, the denominator is just n for both of them. And the numerator is ST squared. So we've got 1 ST squared plus 2 ST squared. So we've 1 plus 1, so we've got 2 ST squareds over n, right? So what is that? That's just the square root of 2 times ST times the square root of ST squared, ST over the square root of n. That's it. Okay. All right. Any questions on that? Do you want me to go through the different? Seems like I'm beating this around. Why have we spent so much time on this? Let's just skip this for now. Let's skip this. We're going too slow. We have to catch up. Okay. I know this is probably really boring for you by now. Any questions? Any questions, Al? I really don't want to overcomplicate it. The whole point of this was for you to just get the intuitive idea of, remember, our basic formula. Okay? So let's just maybe do this. So let's just do that. Let's remember our basic formula. So we have this basic formula. It should just be easy for you to remember, okay? You have some effect size. You have this difference. And that's just the effect size you want to detect, okay? So let's just write that. That's our effect size. The difference between the alternative and the null, okay? That's real intuitive to you. Then we have the Z alpha plus Z beta, and that's the difference, that's the size in terms of standard errors. And then to change this to the units of that, we multiply by the standard error. That's all we're doing for our sampling error. Okay, that's super easy. That's the power formula for everything. Why they look complicated is because of these standard errors can get extremely complicated. That's why they look complicated, but this is all you're doing. This is the basic idea. So let's just do it for these two simple situations. For a one sample average problem, like our first, and a two sample, like what you had in the homework, okay? Or what you're going to have in the homework with the flu vaccine. All right, so for two sample average and for one sample average and for two sample average, or percent, you'd have to multiply to a slight variation on this. So what do we have here? So for this one, they start off exactly the same, look. Right? All right, so we've got that. And so now, we just change that standard error to SD over the square root of n. That's what we're going to do. All right, SD over the square root of n. And now we'll just solve for n. So what's the square root of n? Is going to be z alpha plus c beta. I'll just go through it slower this time, right? Times the SD over d, right? And then when you square both sides, you get, you don't have to, you could solve for square root of n, do this first and then square, but if you want to do it this way, you just square everything. Okay, so that's what we've got there. Easy. Now, how does it play out for the two samples? See? So instead of this, I'm just going to put that on. And you'll see what you're going to end up with is just a 2 here. Instead of, we can just go through it. So this is, now we have z equals c alpha plus c beta times, this is assuming that, you know, the sample sizes are the same, times square root of 2 times SD over square root of n, right? So now we do the same thing, square root of n is equal to z alpha plus z beta times square root of 2 times SD over d. We square everything and we get this. So we get the same thing. Now, what is n? Let's look at, I just want you to see right here. This n, just don't get a little confused, is what? For each sample. I'm saying they're the same, so it's for one sample. So you have two samples here, so just be careful about that, okay? So n is the sample size for each group. And you have two groups. So each group is twice as big as it would be in the one sample. So each group is twice as big as for the one sample formula. And since you have two groups, your whole experiment's going to be 4 times as big as if you did a one sample experiment, that's all. Okay? So the total number of subjects two groups, each twice as big, is 4 times as big as for one sample problems, situations. Okay, that's all. All right, so that's the idea there. Any questions on that? And let's see. One typo here I think we should correct. I made a typo here. I should have, this difference, the way we're, the alternative is bigger than it. So this distance this is positive. And here I say z alpha minus z beta. Well, that's if you're writing, easier to think of just adding them. and then just make Z beta positive. Take the absolute value of Z beta. It's just easier to think of it as a distance that way, instead of saying subtracting the negative. Okay? And then, so here's our example, and let's get rid of, that was a typo, there was a square in there. Here I did it minus, see here it's the same thing. Minus the negative is just the positive. All right, and so this is good, where D is, whoa, H, this is, somehow things got mixed up in the press here. Okay, that. All right, does that make sense? Does that make sense? All right, we got it. It's not really that hard at all. If you think about it visually, it's not. Yeah, in the back. Did I make a mistake? That's all right. Good, I need to block anyway. Go ahead. Oh, let's see. Okay. So far away, it's hard to see. Close, close. It's so. Yeah.
So
I'm just going to turn, her question was just, she wanted me to turn back a page so she didn't catch anything. So I'll do that, and yeah, go ahead, and is this, can you see, is this what you wanted? Are you good now? All right, what was your question?
So basically, on our homework, when we're asked to find this, and these are gonna be like the formulas that we use after.
Uh-huh.
Okay.
Yeah. Yeah, you can just, if you ask to find the n, you can just use this formula, or if you want to just practice in general, I think it's like, I always like to go back to the intuitive stuff, because what if I don't give you that on your, you don't usually get any formulas on your exams. So it's, I mean, yeah, you can memorize that, but I think it's easier just to go back. All right, any other questions? Okay, let's take a deep breath, because we are going to do part 2 today. We're behind right now, a little bit behind, so we're going to just have to try. We only have 1 week to do this part 2, which is on correlation, causation, and confounders. Now, how many people have taken Stat 100? Raise your hand with me, or with Carly, that version, or Uma, or, you know, online, with the notebook. How many people have taken it? Raise your hand. All right, so you probably know that confounders is kind of a confusing subject. Confounder means confusion, so it's obviously confusing. So, but for those of you who've never thought about it before, you're going to have to read this section very carefully, okay? Read everything in this section very carefully. All right, so let's just start off. And the idea, we've just looked at significance tests, and the important point is that people forget is that significance tests don't distinguish between association and causation. We do exactly the same significance tests, whether we have observational data or experimental data. Exactly the same. All right? We compute the same test statistics, the same p-values to test the null hypothesis of no difference between various groups, whether or not that group membership was chosen randomly, like in a randomized experiment, or the subjects themselves or some other non-random method was used for group assignment. So that's because what we're doing, when we're doing a significance test, all we're doing is trying to see whether we can detect, basically, one way of thinking about it is a signal, just some pattern amidst the random variation or not, but not where the signal came from. We're just saying, is there a pattern there? Is there some significant difference between the two groups? But not where that came from or why or anything. So it's a statistical check to see if it's likely that there's any systematic connection at all between the explanatory variable and the response variable. It's not a check to distinguish between different types of connections. Like, if there is a causal relationship, it won't tell you whether, first of all, whether there's a causal relationship at all, and it won't say whether does A cause B? You wouldn't know from that. Does B cause A? Does the confounder cause both A and B? Okay? So you don't know. It doesn't distinguish between causations and associations. So if the test doesn't, if the significance test does, then what doesn't do that, then what does? Well, as we saw in Stat 100, the only thing that allows us to really specify a genuine causal relationship is random assignment. Random assignment of the explanatory variables. Because that breaks any systematic association between those explanatory variables and all other possible causes of the association, possible confounders, okay? So, yeah, what happens? We don't always have a randomized experiment. So, a lot of what we're going to be doing in this class is thinking about how, just through other types of methods, we can, is there any other type of statistical analysis that will allow us to figure out causation? Because remember, lots of times we want to know not just whether something predicts, whether A predicts B, but whether we can change A to change B. And causation means we can do something about it. You might want to, that's a huge reason to want to know whether there's a causal connection, because if there's not, there's no point in changing something. So to answer that question, we first have to remember what it is about those randomized experiments that really allows us to conclude causation, and then see if we can somehow get at that through another way. We don't have to learn it. It's impossible to do a randomized experiment. Okay, so basically, the idea of the what allows us to conclude causation is that if the treatment and control group, if the two groups are randomly assigned, then we're going to eliminate, when subjects are assigned to trip by the flip of a coin, all the systematic differences between the groups are eliminated. Okay? So think of it this way. It's basically, there's balance on all variables before you even assign a treatment. You want the two groups, you'd love it to be the same people in each group. That would be great, right? This is clones. That would be the perfect experiment if they were just clones, a group of people, clones of each other. And then one group gets the treatment, the other group doesn't, and then that's the only difference between the two groups is the treatment. So if you see any difference in the responses of the two groups, it has to be the treatment because there's nothing else. That's the idea. All right? So with random error, you'd think, okay, well, how would a flip of a coin match up the two groups? You'd think, that's crazy. Why leave it up to chance? Well, the idea is that if your sample size is big enough, random errors average out, so there's no systematic biases. Okay? Think of flipping a coin many times. Within random error, the coin balances the two groups on all characteristics that may be relevant to the response, including ones not even identified by the researcher. Okay? That's if you have a big enough sample size. But what if you don't? So we're going to talk about that, how to deal with it when you don't have a big enough sample size. All right. So first let's do an example. And the example that I'm going to talk about is something that actually happened in, we're going to talk about on the next page because it's actually something that happened the first semester, just a few semesters ago when I was teaching this course. I started off the course with hand-graded homework, and I thought, well, maybe computer-graded homework would help people learn. So I thought, okay, think about it. Let's say I have two groups. One's computer graded, right? This is before the treatment. I divide them up into two groups, all right? And I want them to be balanced. And I'm going to, so I divide it up into a group that's going to get the treatment, which is, you can call it computer graded homework. That's going to be the treatment. And the other group is going to be hand graded. I haven't started doing this. I'm midway through the semester, hand-graded homework. Okay, so computer and hand. And what I thought of doing, I talked about it with the class, and there was, to see what they wanted, and about half the class really wanted computer-graded homework, and about the other half really wanted hand-graded. And I thought, why don't I just let them choose themselves which group they want to be, and then at the end of the semester, I can see if the exam scores are higher among one group versus the other. And when I thought about doing that, I realized I looked at the people. Let's just imagine this. I think it was something like this. Let's imagine it was that the computer-graded people had more A students in it. They'd already had 2 exams. They'd already had a lot. These students were stronger. One of the reasons they wanted the computer-graded homework, they felt like they didn't need that individual attention as much. And they were maybe more savvy with computers and so forth. And so there were a lot more A students already in this class, in this group, than there were in this. Let's say that was true. Okay, so then the scales, if I let them choose themselves, the scales are going to be tipped like this to begin with. So the responses afterwards, when I measure their response, right here, we're not going to be in this situation. When the response, this is a situation you'd like, but if it's, you'll see the outcome, and if the computer graded is done much better on the exams than the hand graded, and what I was going to measure was the future exam scores, like the final and the, I wasn't going to take into account the homework, I was going to do the final and the exam 3. And so if this group got higher, well, wait a minute. If they chose themselves and were unbalanced to begin with, you see, I don't know. I don't know how balanced. If you randomize, you guarantee some balance. You can measure this within random error, right? You guarantee that. But if you don't randomize, there's tons of variables that could make it very unbalanced, so that when you get to the end, you don't know if they started off, if it's due to, wait a minute, if there's stronger students here to begin with, maybe computer grading was worse for them. Maybe they would have ended up here, and now it made it like that. It just, you can't tell. So that's the idea. Now, so then I thought, okay, I can't do that. Now, so let's look at this example. So I said, suppose I wanted to, so here's the example. I wanted to see whether the computer-graded homework helps students do better on the exams compared to the current hand-graded homework. And let's say there are only 36 students in the class, okay? And 18 of them had A averages up to that point on the exam, and 18 of them had B averages. Let's just pretend. With only 36 students, random assignment into these 2 groups could result in large accidental differences. For example, I could get just by 13 A's and 5 B's in one group, and 5 A's and 13 B's in the other group. Just by, look, if I didn't, here, you don't know what blocking is yet, but if I just took, there's 18 A's and 18 B's, I just randomly divided it, I could get just an overwhelmingly unbalance here. So even if the computer grading really was better, it wouldn't even show up because these students, the hand-graded students are so much better to begin with. Does that make sense? So it would probably still look like hand grading won out, even if computer grading was better if I did this. Does that? You got it? Okay, so what do? I do something called, how about this? Blocking. And blocking, I explain it here. I say, randomized studies eliminate confounders as long as the sample size is big enough for accidental differences to average out. But with small sample sizes, what researchers do is they block into relatively homogeneous groups first and then flip a coin to decide which treatment, to decide who gets which treatment within each group. Okay, so let's see how that works. So you might think this introduces bias because this is not random. I think, okay, I'm putting here, here's the 18A students. I divide them into 2 groups. Okay? But it really does, and then I randomly divide this. Take out half of the A's and put them in the hand grade group, and half of the A's I put in the computer grade group. And I do the same. That ensures an even distribution along the thing that I think is going to mess up my experiment, the relative, that ensures that. And it doesn't really introduce bias as long as, I randomly, the final assignment to these two is random. That's all that matters. I can do all the blocking I want ahead of time, but as long as the last assignment to both of them is random. Does that make sense? Okay, so that's basically the idea, and so let's write that down. So in small, and you'll see this all the time, in small experiments, people have to be very careful to do they have to carefully block on what they think could affect the response. Okay? You want to block first and then randomize. And, I just want you to know that this does not in any way introduce bias. It reduces accidental error. It does not introduce bias at all. It would introduce bias if I'd gotten to this point. How would it introduce? If I got here, this is what could have happened. I said, oh shit, look at this. This is so overwhelmingly, this is just so unbalanced. I'm going to balance it up. So I'm going to take some of these and switch them around, and I'm going to pick these people. That would introduce bias. Okay, do you see? All right. Okay, and then it's always best to block whether you're to block first. I mean, it never can hurt, but it doesn't make much of a difference if you have a very big sample size. Because with a big sample size, those differences are going to average out. You're not going to get such a crazy uneven distribution. It doesn't make much of a difference when you have large sample sizes. All right, now we have 5 minutes left. I'm racing against the clock here because I really have to, let's see what time it is. 4 minutes left. All right, let's just see what we have to. So you read all these words. And now, I just want to say, look, I'm just going to give you a preview here. We're going to move on to look at, many times we're in this situation, we don't have a randomized experiment. So what can we do? So we do something very analogous to blocking. We're going to go through this next time, but I just want to give you this little preview. What we do is if the students choose, let's say the students chose, and it wound up this way. That's sort of opposite to how I said it would wind up. But let's say it wound up really unbalanced somehow, because the students chose. Well, then what do you do? Then you stratify it. It's like blocking after the fact, and you divide it into the A's. So you compare the A's, even though you can't just look at the average responses of the two groups, because they're so unbalanced. So what you do is you stratify. We did this in step 100. You break into relatively homogeneous groups around the factor that you think is unbalanced here. And so you would say, okay, yeah, there's more. We're going to just compare the A's to the A's, apples to apples within each group, and the B's to the B's. Does that make sense? And that's what you do. It's, so that's the idea. And then we're going to look at some examples of confounding, and just that will be next lecture. Next lecture is going to be really important. Okay?